Welcome to DHC Year 1 Systems Review. Essentially, I'm going to review DHC material that you've been taught in the systems part of the year. Probably has nothing to do with systems per se. So let's get cracking. Next slide is content. So Year 1 and the second part of Year 1 is a little bit less intense in comparison to the first part of the year. So we're just going to cover prognostic studies, which can be a bit tricky to understand. Qualitative research, just one slide on that. A little bit on RCTs. We'll go through a small worked example. And I've just highlighted in red and an asterisk material that's been asked before in first year exams as well. And I'll let you know whether it's MCQ or SAQ. All right, next slide is disclaimer again. I said my first year DHC exams 2 years ago. Things may have changed. I don't think so. I think they seem to have the same sort of pattern of what they want to assess. But yeah, let us know if you find any mistakes or if you want to improve the content. Next slide is end of year 1 DHC exams. So formative Q&As can't emphasize enough that they're your best way to study. And really, really try to remember all of the stats that you were taught in the first part of the year, because that's going to come back in this exam. So yes, in terms of Q&As, focus what was taught in systems DHC, such as climate change, social determinants of health. I think we had a question on that in the SAQs, and also in rural health. But everything else that's stats related from first year is going to come up in some form in SAQs and MCQs. So in first year, we had an SAQ. I think it was the first page of the short answer exam. It was quite devastating. It was an abstract or a description of an RCT, which I thought it was an RCT. And then there was a question what kind of study is this and why, and then they got you to calculate or interpret certain numbers. So prepare for something like that. And MCQs are going to be, again, a little bit more stats heavy. There's going to be talk about ratios and which ones are calculated for which study designs. Again, if you're not sure what that means, go back to my first lecture. I thoroughly go through that for the year 1 lecture. So they'll need your knowledge about study design. They'll need your knowledge about calculating sensitivity and specificity. But aside from all this hard stuff, there's going to be really easy marks on risk factors. So, identify out of the following, identify a risk factor for cardiovascular disease. So that's going to be an easy one, depending on what's on there. Like you could, a lot of these questions are actually DKHI related, so they should be fairly easy for you. And don't overthink them. I've had students overthink them and Google them and PubMed and be like, well, technically all of them are risk factors. Don't do that. Just go for the most obvious answer, and it's probably right. And prevention questions. So your usual question about which one of these is primary prevention, something like water fluoridation. Okay, so that's a little bit on that. So next slide is on prognostic studies. I myself found them quite difficult to understand in first year, and it's taken me several years to kind of slightly grasp what they're on about, but they're still quite challenging to understand. So if you struggle with them, that's absolutely fine. You just need to remember certain definitions for first year to pass. So I'm going to go through the definition, the types of study designs, the difference between risk factor and prognostic factor, methods for describing prognostic risk, and a little bit on biases, but biases are not that important in first year. They're going to be more important in second year, so I'm really going to brush over them. Okay, so next slide is the definition. So we all know that prognosis is a likely course of a medical condition. So I think I find it quite helpful to think about prognostic studies in terms of you have cancer or someone has cancer and they come to an oncologist and they want to know how long have they got to live. That's the sort of case study we can go on when we think about prognostic studies. So let's say I have leukemia and I've come to the oncologist or hematologist and I want to know how long I've got to live. So oncologists are actually experts in prognostic studies. They know all the prognostic studies that will tell them how long have you got to live or how long you've got to live on a particular treatment. So that's essentially what a prognostic study is. It identifies factors that influence your survival after a particular diagnosis or treatment if you're getting chemo, for instance. So I found this, the graph that I'm showing is, I think, from the British Doctors study, where before they knew that smoking caused cancer, they just tracked doctors who smoked, I think, over time to determine their survival, and they noticed that non-smokers lived longer than smokers. So that's essentially your survival curve or your survival study, where on the y-axis you've got survival, and on the x-axis you have time until event, and the event is usually death. And usually the study design for a prognostic study is almost always a cohort study. And remember, cohort studies where you recruit a bunch of people and you follow them over time until they develop an outcome. So an outcome in a prognostic study is usually, if not almost always, death, because it's the most objective thing. There could be an RCT that's a prognostic study. Usually pharma companies would study a new a chemotherapy drug or any anti-cancer drug, and they want to compare it to the standard treatment that a person's receiving. So that would be an RCT. And prognostic studies oftentimes have really confusing names. So they have multiple names. They could be called a prognostic study, they could be called a study of prognosis, or prognosis research, or simply cohort. And once you read a cohort study, half the time you realize, oh, this is a prognostic study, but essentially they're interchangeable. All right, next slide is the features of prognostic studies. So cohort is really important in a prognostic study, and potentially the most often cause of bias in a prognostic study. The people who you recruit for a study, let's say you recruited a bunch of people with leukemia, and you're exposing them to a new leukemia drug, exposure plus, to a standard leukemia drug, exposure minus. And you're tracking them over time to see, tracking their death rate essentially, to see which drug is better than the other, or whether they're the same. When you're recruiting these people with leukemia, you want them to be as homogeneous as possible, or as similar to each other as possible. You don't want one person to be in the early stages of leukemia, because that person by definition is going to take longer to develop proper cancer and then die, versus someone who's essentially being palliated because the leukemia is so bad that they're essentially going to die. You can't recruit those two people into the same study, because they're going to skew your results. One's going to die sooner, one's going to die much later. So you need to sort of find these people who have similar staging, similar symptoms, that they're similar enough that once you track them over time, they're going to die roughly, you estimate for them to die roughly at the same time. But the treatment is the difference here, and the treatment will determine whether one dies sooner or later. I know this is a really grim topic, but that's essentially prognostic studies for you. So exposure that we're talking about is time. If you want to do a control, in a control group, there will be essentially time and nothing else that's stopping them. But in a treatment group or an intervention arm of the prognostic study, you usually get treatment, something like chemo. And outcome is usually death. And then you get prognostic factors. And these prognostic factors are factors that influence the outcomes, such as length of the chemotherapy or stage of your cancer. It is essentially a covariate, and it's very different from a risk factor. And let's talk about that a little bit more in the next slide. So you've got your intervention, which is chemo. You've got your outcome, which is death. And then you've got your risk factors. So the risk factors are up top, and sometimes they're referred to as mediators or moderators. I've never heard those words before, but they are risk factors. And risk factors, by definition, are associated with causality. I don't know if you remember in the first part of the year 1 lecture, I talked about the risk factor model of disease. And you've got like, I forget what they're called now. That's it, necessary and sufficient risk factors. So again, risk factors are invariably linked with the disease that they're causing. That's not something we're concerned in prognostic studies. In prognostic studies, the disease is already there. We're not concerned with what's causing the disease. We're concerned with how long it takes you to die from that disease. So a prognostic factor if you look down below, is something that only affects and influences the outcome or your death in that case. And a confounder is something like age, where it influences both your intervention and your outcome. So age is a common one, or gender is a common one as well. Obviously, the younger you are, the more likely you are going to tolerate chemotherapy, and the later you're going to die. And if the older you are, the less likely you're going to tolerate chemotherapy, and the sooner you're going to die. So age is a common confounder, but a covariate, a prognostic factor, is something that influences your outcome or influences your time to your death event. And that could be something like length of chemotherapy or stage of your cancer. And prognostic studies are very interested in identifying these prognostic factors, because then they can modify them to lengthen your life. If that makes sense. Essentially, all of this is a little bit low yield, but I wanted to explain the logic behind it so you don't get bogged down in the detail. All right, next slide. Let's talk about methods of describing prognostic risk. You need to know what the Kaplan-Meier curve is, and we're going to talk about it. And then you need to define all of these rates. 5-year survival rate, you need to be able to define it in an SAQ. Not so much for the cumulative survival rate, but you also need to know what a median survival is and hazard ratio, and how to interpret it as well. So let's talk on the next slide about the Kaplan-Meier survival curve. So if you look to the curve, we've briefly talked about it, but the Kaplan-Meier curve is a very characteristic curve. It's essentially a step ladder, sort of a ladder-looking curve, and it always looks like this. Sometimes when you have a lot of people recruited into the study, it becomes almost like a smooth line, but it's still a little bit jagged. You can see it, and we'll see that in a couple of slides. So always on the y-axis, you've got survival, usually as a percentage or as a ratio, and time is on the x-axis until an event. So every time you step down, you reach a new event, and then every time the line is parallel to the x-axis, that means the time goes by until another event is reached, and then you step down again. Usually there are two groups that are being compared. If there is a huge difference between two groups in survival, you will see a gap between the two lines. If the gap is very small, that means there isn't much difference between the two groups. And just to mention, it's a non-continuous stepwise observation, which means by definition it's non-parametric, because remember, parametric uses continuous variables and fits a bell curve. This is far from it. So it's very non-conventional, or not your usual parametric statistics. And again, it deals with incomplete observations. It was developed to deal with that. And I've explained why in x-axis. So let's go to the next slide. So these are the variables in the Kaplan-Meier curve. Censoring is an important and distinguishing feature of the analysis. Essentially, anyone who's censored is a patient who's dropped out, or has been lost to follow-up, or doesn't experience the event, and that's usually towards the end of the study. So basically, when you see the curve lines trailing off, they become very messy because so many people haven't reached the event and they've just essentially taken them out. We'll see that in a couple of slides. So when you start, let's start from the beginning in the graph. So you're looking at 8 people, and these 8 people represent 20% of survival from cancer. So 8 people remain in the study, and 3 are censored. And you usually remove the censored people because they're not, isn't 3 within the 8, because they're no longer counted as, because you can't track them, you don't know who's going to die, so you essentially need to remove them. So you go 8 minus 3 over time, 5 people remain at risk, and 1 of these people die. So out of these 4 people remaining who are alive, again, you have 2 who are censored, or 2 who have dropped out, a lot have been lost to follow-up. And that means 4 minus 2, you have 2 remaining at risk, and that's your sort of third one down along the line. But how do you calculate the new survival rate? So the survival rate used to be 20%, but the new current survival rate is actually 4 out of 5. And remember, 5 is because you've removed 3 out of the 8 because they've been censored. So the current survival rate for the 5 people is 80%. But to make the maths work, you need to multiply 20 by 80. So the new current survival rate is actually 16%. And that's how you drop the line down. Again, you don't need to know this. I'm just walking through an example to show you how it's calculated and the importance of censoring. You will never have to calculate something like that in the exam conditions. At least I haven't seen it happen. But that's kind of the logic behind it. All right, next slide is cumulative survival. So it's essentially what I've just described to you, the 16% that was calculated in the previous slide is cumulative survival. And this table shows another way to calculate it. So if you look at the first row, time interval, let's say that's a year, 7 people are at risk of dying and they have cancer, and none of them dropped out, so that's 0. So that means 7 people are at risk. 1 dies at the end of the 1 year. That means 1 out of 7, 14% deaths, and then 86% survive. So your new survival rate from, say, 100% is now 86, and that's how you do the drop down. And then you continue, let's say the next time interval is 4 years, 6 are at risk, 2 have been censored because they've dropped out or can't be followed up, which means you now are working with 4 people who are at risk. 1 dies, 1 out of 4, 25% have died, 75% remain, and then you just multiply to get the new cumulative survival, and it's now at 64%. And you keep going like this until you get your full curve. So it's not too hard, but obviously every time you think about it, it takes a while. So again, not very important, just thought I'd explain the logic. Next slide is important. These are the definitions you will probably need to define in a short answer question, and if not, at least recognize them in an MCQ. So 5-year survival rate is the proportion of people still alive after 5 years of follow-up or 5 years post-diagnosis, depending. Cumulative survival is what we've just done. It is the proportion of people remaining event-free or death-free past a particular time interval. Median survival is the time after which half or 50% of the patients are alive and 50% are dead. And hazard ratios are the probability that an individual would experience an event compared to a control. So hazard ratios are quite similar. They are probability ratios, and they're quite similar to something like an odds ratio. And we'll talk about it a little bit more in the next slide. All right, putting it all together. So I really like this curve. I've left a link down below, studentsforbestevidence.net. They don't cover everything that we study in DHC, but I quite like some of their articles because they break down and dumb down certain concepts that can be a bit difficult to understand. So if we look at this curve, again, familiarize yourself. Y-axis, patients surviving. This is probably a survival curve. X-axis is time. Okay, let's look at the red one. We're going to talk about median survival. So 50% patients survive, that means, and 50% are dead. So if we follow along to the green line, at 906 days, 50% of patients survive in the green curve, whatever that curve means. But then as you follow on to the blue line, at 2,246 days, 50% of patients survive on the blue curve. So there is a drastic difference between survival time between two curves. One survives for much longer than the other. So that's essentially what the median survival gives you. You can also do the 10-year survival. So for us, they're usually interested in 5-year survival. So you would go down below where it says 5 and look up and then look at the percent of people surviving. But here they're looking at 10 years. So let's find the 10 years, blue down the bottom, walk up, blue line, 45%. And then that would be different for the green line, but they've just reported for the blue line. Okay. And what else? So yeah, that's what I meant about the censoring. See those dashes towards the end, the red ones for both curves? That's essentially all the people who have been censored, and they're probably the ones who didn't develop the outcome, which is death. All right. Let's talk about the hazard ratio. So hazard is calculated somehow probably in some way similar to an odds ratio, but because they're non-parametric statistics, they're probably flipping numbers around. I don't understand how hazard is calculated, but all you need to know is that hazard in an intervention group is divided by hazard in a control group. And we've seen this before in ratios, okay? So we need to know that if we're looking at a number that's hazard ratio 38%, that means intervention group is more likely to experience something than the control group, right? So that hazard ratio 38 means 38% of patients in the intervention group were more likely to experience death versus a control. But whenever you're talking about something that being more likely that's less than 50%, it actually is easier to flip it around and say less likely and subtract from 100. So it's the same thing as saying 62% of patients in the intervention group were less likely to experience an event such as death. And that's essentially all you need to say from your hazard ratio interpretation. And that makes sense. If you look at the curve again, the blue line, 0.3%. So that means fewer people are dying in the intervention group than the control. So that's essentially all they're saying. 38% of people are likely to die in the intervention group, or 62% are less likely to die in the intervention group. And as you can see, the confidence interval is significant, and so is the p-value. I think for this confidence interval, it's important for it not to cross 1 because it's a ratio. So it doesn't cross 1, it's significant. If it was an RCT with a risk difference, it's important for it not to cross 0. Okay, let's go to the next one. Prognostic study biases. Again, I wouldn't worry too much about them. You just need to know a couple and understand what they mean for the purposes of the exam. This will become more important in second year, so don't completely dismiss it. It will haunt you forever. But yeah, for now, just remember that selection bias occurs when you're selecting patient samples, and measurement biases occur when you take measurements for your measures. So non-representative sample is probably, again, a very important one for prognostic studies, because let's say you are recruiting these leukemia patients and you're recruiting them from the Leukemia Foundation. And then you decided to go, you haven't recruited enough, and then you decided to go to your local GP and recruit a couple more. The people who are recruited from the Leukemia Foundation, your tertiary care centre, are going to be way too sick than the people that you recruit from the GP. So there's going to be discrepancy, and the ones that you recruit from the Leukemia Foundation are probably going to die sooner. So don't do that. Don't collect in a non-representative sample. You need to collect samples that are from a centre that is not too tertiary, which means they're not going to be too sick, or at least if you do that, at least make sure that they're all from the tertiary centre, and then say that, yeah, okay, I'm expecting them to die sooner. Lag and lead time bias are the ones that I was talking about earlier. Don't include patients who are too late or too early in their diagnosis. So lag too late and lead too early in their diagnosis. Make them as even as possible. So leukemia patients who are all around, 40 years old and who have similar staging or similar life expectancy. And attrition is, loss to follow-up is always an option in anything that you talk about to do with biases. Measurement biases, we talked about confounders. So if you haven't measured confounders such as age, that's a massive one. You have to account for it, because if you're recruiting patients who are 20 and 80 in the same study, there's going to be discrepancies. Subjective reporting, so essentially I've seen some studies not using death as an endpoint, and essentially that's, unless they justify it really well, it's almost always bad, because death is really objective. Once you have died, you can collect that number and you can track it over time. But if it's something else, it becomes less objective and more subjective. And ascertainment bias, which is, make sure that follow-up is the same for all patients. Don't just follow up people with the drug treatment and don't follow up the ones who are the controls without it. Okay, so again, remember one of each. Remember non-representative sample or lag or lead time bias and unmeasured confounders, and you should be fine. Okay, qualitative research. Next slide. There's not much you need to know about qualitative research, I think, for year one. You may have a lecture on qualitative research. But essentially, all you need to know, and the word systematically seems to come up in answers to qualitative research questions. So I think a lot of people dismiss qualitative research as something that's wishy-washy. But what DHC wants to teach us, and I think they're right in that, is that qualitative research is a systematic way of looking at data. So you can't just collect focus group answers and just publish them. You won't be able to. You need to systematically go through them, code them, create a theory or some sort of thematic analysis before you can present that information. So qualitative research, again, systematically answers the what and why research questions. And what I mean by that is that as soon as you see in an exam situation that a research study wants to understand what people do when they receive the diagnosis of cancer, or why do people seek alternative medicines for their cancer treatment, the what and the why essentially are your trigger words to identify this research question as a qualitative research. Sampling, know a couple for the exam. Know that there is no set number for qualitative research as opposed to quantitative. For quantitative, you just know, okay, I've done my power analysis. I need 150 patients for this statistical significance to work. It's not like that in qualitative. You aim to keep the number as small as possible, but there are different ways of getting there. So criterion sampling is essentially picking cases to meet some sort of criterion. So let's say I'm gonna analyze the data as soon as all of the patients have answered my survey. There is no set number. I'm just waiting for after a year for these patients to answer my survey. Snowball and saturation keep coming up in I think MCQs. So snowball is when existing study subjects recruit their future subjects through acquaintance until no more subjects can be recruited. And saturation is you keep recording information until you see that there is no more new information being recorded. So let's say again, you're studying leukemia, people with leukemia, and you keep recruiting new patients who have leukemia, but you realize that you thematically have covered all of the things that they have been saying. So you can now stop. You need to know a little bit about study designs, but essentially know that there are things like phenomenology and field research. So field research is when you go out there and you integrate into a part of a community. So I knew a person who did qualitative research in even evangelical women in London. So she attended all of their events. And she took notes. So maybe it's not field research, maybe it's something else. But essentially, yeah, she's in the community with them, taking notes and observing everything that they do. So that's a form of study design. Again, it's a bit less yield. I don't think that you're going to get asked many questions on that, if any. But you need to know what data collection methods are common in qualitative research. So something like interviews, observations, and focus groups especially. And data analysis, again, like I mentioned, data are coded, patterns and data identified, and themes are created. And this theory that is created from the themes needs to be generalizable to the wider population. And again, there is structure and systematic process that informs validity and reliability of your theory of what you have done. There's going to be more on everything that I've just said in year 2. And we're going to talk about biases and stuff like that. So that's essentially all you need to know for the exam. Okay, let's move on to RCTs. So your RCT study design, you sample a population and you randomize it. I really like that they've put a dice there, because it's, you roll the dice to randomize people into group 1 or group 2. The beauty of RCTs is that people are so randomized that there is nothing else. And the differences between the two groups are randomized enough that there is nothing else that can account for the difference between two groups except the treatment that you provide them. And then again, you randomize people to an intervention arm and or control arm, and that control arm could be a comparator to a standard treatment. And the beauty of RCTs is that they're almost always, I think always, are blinded, and it's even better if they're double blinded. And what I mean by that is that patients don't know what drug they're receiving, and if they're double blinded, the doctors who give them the treatment also don't know what the patient's receiving. That's just the gold standard. And then you track them over time for a particular outcome. Usually when I think about RCTs, I think about drug trials. So people are given two randomized groups of people get given a drug versus a placebo or a standard treatment, and they're tracked over time to see if they developed an outcome, whether it be lowering of blood pressure or improving in body mass index. And this is the first time I sort of touch upon minimum clinically important difference, which I think Leonard is a huge fan of, because I think he does RCT studies and he may have given you a lecture on it. And I think that's an important concept, not just for the exam, but just for life in general. Minimum clinically important difference is the smallest change in treatment outcome that a patient would identify as important. So what do I mean by that? So let's say we've got an RCT study that shows a difference between two groups and that it is significant. A difference between two groups in an RCT study can have the same mean, but variable standard deviation for individual means. And the variance in the standard deviation can be enough to cause the two groups to be statistically significant and statistically different from each other. That means that if, group 1, the mean's the same for their blood pressure, group 2, the mean's the same for their blood pressure, but there is enough of a variance between the two that the groups are statistically significant. That means the people who come out from the study will say that, well, I didn't feel any different. I thought I was getting a placebo, or I thought I was getting an intervention, and I still feel fine. And that's essentially what that concept means. Will the change that the scientists have found as being statistically different actually be clinically meaningful to the patients? And a lot of the times, because statistics deals with such minute numbers and minute differences, a lot of the times these differences do not matter to patients. And I think that's why there is now a huge surge in quality of life questionnaires and research, because we need to know if patients are actually satisfied, or if there is any change to their well-being from the treatment that they've been given. Okay, and I think one more thing, I think this will either come up define what this means in an SAQ or an MCQ. You just need to pick the one that is most appropriate. Next slide is on different types of RCTs. I don't think necessarily you need to know what they mean. I don't think we've ever been asked. Usually we just need to know that for superiority trials we need to use intention to treat analysis. But I thought this graph looked cool and explained the three concepts quite well, so I thought I'd include it. So with different types of RCTs, so superiority trial and non-inferiority trial and equivalence trial are essentially ways to compare two or more treatments. And you have a cutoff, which are the dashed lines outside of number 1 in the middle. So you've got the cutoff where you think beyond this point, this treatment is superior to standard. And the one on the right-hand side, the more dashed one, is the cutoff point where a treatment is more inferior or just inferior to standard treatment. So superiority trial is taking the drug better than doing nothing. And A shows that the line crosses the dashed line, which means new treatment is superior. And it can't cross the number 1 because number 1 is the standard treatment. And non-inferiority trial is drug no worse than the standard treatment. And again, it needs to cross, it can't cross the inferiority margin, because below that we won't accept the treatment. An equivalence trial is the drug is no better or worse, and it needs to sit between the two dashed lines. Again, I don't think I've ever actually come across these particular definitions when I read an RCT. I think it's just highly conceptual, and maybe Cochrane deals with these more than anyone else, but Just know that they exist and what they look like. All right, next slide is, so RCT analysis, Leonard seems to think that we need to know intention to treat analysis. So with intention to treat, patients are randomized at the beginning and outcomes are measured from the randomization that you receive. So basically you're allocated to group 1 or 2, and regardless of whether you've taken the drug or have stayed in that study, you still, all the outcomes are pulled together and they're analysed. So it's a very conservative analysis and biases towards a null effect, so no difference. But it's also incredibly powerful because if your study shows with intention to treat that your drug works, and actually probably does work because it skews so much to no difference, and if you still show a difference, that means it really does work. And it should be performed for superiority trials, and I do remember MCQs on the two, like which one of these should be used for a superiority trial, and it's intention to treat analysis. And then you also need to know per protocol analysis, which is used for non-inferiority trials. And per protocol analysis is more biased because it analyzes people who took the drug, not who have been allocated to randomized groups. So for instance, let's say a person in group 1 took the drug and then decided they didn't like it because they felt like they had a placebo. So they went to group 2 and decided to take what they thought was an intervention, and then they stayed in group 2. Tracking within RCTs allows that to happen, so you can that person. I don't know how it works, but basically you make sure that you count these people and you analyze them in accordance to what drug they've taken. So basically, not because they were in group 1 initially, but you analyze them from now in group 2, which the intention to treat doesn't do. As you can tell, it's more prone to bias because you're not respecting the randomization process. And that's essentially all you need to know. So next slide is critical appraisal of RCTs. So I think Leonard may have introduced you to Rambo, recruitment, allocation, maintenance, measurement, blinding, objective, and results. So again, recruitment, you need to make sure that study groups are comparable to make the randomization work for you. And randomization should be done using a computer-generated code, and it should be done at a central location to minimize bias. Allocation, groups should be treated equally, otherwise there is an allocation bias. Maintenance, make sure that everyone's treated the same as they go through the trial, that the treatment is blinded and the clinicians are blinded, and that you use objective tools. So not just quality of life questionnaires, you also need to be measuring things. And allowable loss to follow-up is around 20% in RCTs. And again, with results, you can talk about intention to treat analysis because it's less biased. You need to discuss your outcomes, whether they're ratios, p-values, or confidence intervals. You need to mention that the results are clinically meaningful, and if there were any adverse effects. And you also need to maybe have a look at type 1 error or type 2 error. So type 1 is multiple comparisons, makes you prone to get a significant result when there isn't one. And type 2 means you've undersampled and you got a non-significant result when actually you might actually have a significant result. Again, this is all for year 2. Don't get bogged down in detail. This is an introduction to what you're going to experience in year 2. And RCT biases, again, you might have to list 1 or 2 for your exam, but that's again more important for year 2. So with selection bias in RCTs, there is volunteer bias. Generally, people who are more healthy and have fewer comorbidities are the ones who volunteer for RCTs, and external ability becomes affected because of that. You can't generalize to population of unhealthy people if you've only studied healthy people. Loss to follow-up, so essentially it can overestimate the treatment effect, especially if you don't use intention to treat analysis. Allocation bias, so essentially if the randomization is not blinded. And measurement bias, using ascertainment or detection biases, and you have different outcomes being measured in different groups. So essentially measure the same outcomes between 2 groups. There's performance bias, so different exposures between 2 groups. So I don't know if you're trying to do some sort of crossover analysis in RCTs and you just, you've tried to do something really complicated and then you realize that both your groups have been exposed to different things and there's no way to untangle that. Blinding is important. Again, you make sure that your patients are blinded to the treatment they're receiving and most importantly the doctors who give them the treatment. And selective reporting is also an issue with RCTs where only papers that show significant results are published, which means there is a whole unpublished amount of literature out there where a study has been run but it has shown a negative result but it has never been published. Okay, next let's just quickly review ratios. So with RCTs you're probably going to be dealing with a risk difference, which is your absolute risk reduction. And remember from the first lecture that I've done in year 1, you are essentially subtracting cumulative incidence in the control group from cumulative incidence in the intervention group. And if you get 0, that means there is no effect, but usually there is something, and it's a percentage or a ratio of point something. If you can't remember, go back to the lecture. I explained it quite thoroughly. If you can't remember what cumulative incidence is, that's okay. Go back and figure, it's a ratio. It's not it's a proportion, not an incidence. And then in terms of numbers needed to treat, you just need to know what the definition is. Number of patients needed to treat in order to save one life. There is also numbers needed to harm, number of patients needed to harm to save one life. So usually that links to adverse effects in RCTs. And you just need to know that entity is 1 over absolute risk reduction. And I think we've had to calculate that in the past in year 1 to show your understanding. All right, next slide. Let's go through a worked example. So I hyperlinked to the paper in the paper answers, but if you can't find it, it's in past year exam papers for year 1, and it's DHC paper 2016. So you're going to be given something like a little bit of a blurb. So according to the data from this institute, 5-year survival rate of melanoma increased from 86% to 91%. So in this question, they ask you to briefly define what a survival rate is and then explain what a 5-year survival rate is. So again, they're checking your understanding. Do you know what these numbers mean and what these definitions mean? A survival rate is a half a mark question, so you essentially need to say it's the number of people who survive from a disease or something like that, for a specified number of years. And that's essentially it. And then a brief explanation of a 5-year survival rate. So this is a poorly written question because you don't know what it's referring to, the 86% or 91%. But essentially, you could do either or, and I don't think they'll penalize you because, again, it's a bad question. But you need to really break it down, and you could say something like 86% of people survive after 5 years post-diagnosis of melanoma. Or you could break it down even more and say 86 out of 100 people survive after 5 years post-diagnosis of melanoma. Or you could flip it around and say 14% or 14 out of 100 people die from melanoma after 5 years. So that's essentially it. Next one, more questions. Indicate 2 biases that should be addressed when reading and interpreting prognostic studies. It says you don't need to explain the biases. Essentially, you just need to name 2. So I would use something like, we talked about lag or lead time bias. That would be your selection bias. And something from the measurement bias, such as unmeasured confounders. But I think when I looked at the answers, they just said selection bias or measurement bias, which is fine, but knowing DHC, they probably now want the exact things, so just use the exact things. Okay. Next slide is another worked example. It's a part of the same paper. I'm just kind of showing you what might be requested of you on the exam. So, published data reveals a small but significant number of cases who first present for diagnosis and treatment when they have advanced melanoma. You want to know more about this group and why they present late. And then they ask you what type of study is most suited for this type of research question and explain why. So why they present late kind of makes you think, oh, it sounds like qualitative because it's got a Y in it. And you're right, type of study would be qualitative. And the reason for that is that they, again, use the word systematically. They systematically wish to assess why people present late for treatment and diagnosis when they have advanced melanoma. And that should be good enough. Write a concise research question for the above study. I think I've truncated the more information above this example, but I think it was to do with stage 4 melanoma. So you would say something like, why do people with stage 4 melanoma present late for treatment and diagnosis? That's your question. And I think the key here is to be specific and to incorporate stuff that they've told you. And how do you achieve appropriate sample size for the study? So you could talk about criterion sampling, snowball sampling, or saturation approach. And I think they gave you an example in the answers. They wanted to say saturation approach. And yeah, because you keep recruiting until no new information is emerging. And you actually need to define it in this instance. So I think in DHC, the more you can write, the more you can explain yourself, the better it is. Because if you under-explain, you'll get half a mark. If you over-explain, at least you'll get full marks. So at least, I don't know, maybe more than half a mark, 3/4 of a mark. All right, next slide is, so we had an RCT style question that was similar to the above, and it was an ACQ question. I think, again, I'm scratching my brain, it was 2 years ago, but it was an abstract or a passage about a research findings. And I think they did ask us, what kind of study design is this and explain why. It was a randomized control trial because it included an intervention arm and a control arm and an outcome. And maybe it was something like, this question is best answered by an RCT because, you want to look at an intervention and a control and a defined outcome. But essentially, you need to know what an RCT includes before you can answer that question. And then the thing they asked is what this confidence interval means. And remember, a wide confidence interval is non-precise. And if it's a risk difference, it crosses 0, it means it's not significant. If the CI doesn't cross 0, that means the findings are significant and you can actually write that out. And remember, you don't need a p-value if confidence intervals are provided. They're the same measures of significance. So we, in year 3, critical appraisals, we had a couple of students get confused that when they were reading papers, they couldn't see p-value, so therefore they couldn't make a judgment of whether results were significant. You don't need p-values. Confidence intervals are now overtaking medical research and are the preferred way to state significance in a research study nowadays. I think we were asked to define numbers needed to treat, and the definition for that one already. And then we also needed to calculate the number needed to treat, but before we could do that, we needed to calculate the ARR from a table, and then essentially that was a ratio, and then you said, well, NTT is 1 over this ratio. So it can get a bit complicated because you don't need to calculate it with a calculator, but you need to show it, then you know how to achieve that number. So I think that's essentially what we got in first year. So essentially, if you've been taught prognostic studies in RCTs, it's going to be either or, right? So best to know both. Next. Okay, so finally, study and exam tips. We've already talked a little bit about this. Review your formative Q&As, especially for systems. Commit certain concepts to memory, such as study design, specificity and sensitivity, ratios, and how to read graphs, especially Kaplan-Meier graphs. These are easy marks. Like, do what you need to do to remember these, whether you want to use Anki or you just want to, talk at a friend about it. But like I said in the first lecture, there is a level of rote learning that's expected. And I think a lot of people get really upset that, they study DHC 1 or 2 days before the exam and then nothing makes sense. Well, it's rote learning. Like, it takes time. And do past exam questions. I think I saw either on the first or second year page that someone shared like a compiled document of all the past DHC exam questions. I think that's an excellent way to learn. Definitely download it, print them out. I don't know if you guys got like an electronic exam or a written exam, but definitely practice answering those questions and try to understand what DHC wants you to say. Usually there is a particular way they want the questions answered, just like in DKHIs and DLAP. So figure out that logic and give them what they want. Be comfortable with reading research abstracts and understanding what the numbers mean, but don't go overboard. DHC just wants you to show them that you understand basic concepts, and hopefully this lecture has provided a little bit of an insight of what they want. Definition of a particular term, and then just showing them that you know what the numbers mean. And don't be afraid to answer MCQs with common sense. There are often questions about exercise being a good, a protective factor for disease. And these are easy marks. Like I remember there was a student who, I think I already told the story. Don't overcomplicate things. If you think their answer is that based on your DKHI knowledge of risk factors, just go for it. And yeah, I've already said this. There's always going to be hard and strange questions in DHC. I think we had a question, an MCQ question, that no one could comprehend at the end of year 1 2 years ago. And it ended up being taken out from the exam because people essentially didn't understand it. And I think the results were all over the place. So that's a possibility. I think there was one question about the alma mater something declaration that, again, no one knew unless they studied public health. That's okay. Just leave that one be. If you cannot answer 2 or 3 questions like that, but you can answer confidently everything else, you should be fine. All right, next is image acknowledgements, and finally, good luck, guys. Thanks.